I'm recording. All right. All right. So are we ready? As ready as you can? All righty. All right. So we are pretty much done with propositional logic. Okay. Um, and the only thing I still need to go through is the last example, right? Because I made a mistake, when I was working on it. So that means I can just kind of go straight back to the example and then illustrate, how we can do the resolution. So I am going to cheat a little bit and just start from here. Righty. So now we have this and start a new file. All right. So this is, so we have to go back to psi, which is a CNF representing everything that we know is true. And this is the portion. So let's go ahead and rewrite that here. So psi is not P or R and not P or not Q. So last time I made a mistake of forgetting that Q is negated, and that's why it did not resolve. Well, it doesn't resolve, it did not resolve to false. So now we put this over here, make this always visible. And then we scroll down to phi prime. Okay, this is phi prime, which is our second example. So phi prime itself, or the negation of that, is P and Q. So you can basically write P and Q like this with the extra parentheses, just so that when we make a concatenation of all four, it is clear that P is a disjunctive term by itself, and then Q is also considered a disjunctive term by itself, which also basically means you can always just add a or false with each one, so it is clear when we have to perform resolution what is left after a resolution. So now we say, okay, what about psi and the negation of phi prime? So now that is just the concatenation of the two CNFs. So when you concatenate a CNF with another CNF, it is still a CNF. All right, so I just said something that seems to be obvious. What did I just say? Whoop. Yep, yep. Because each CNF, because each CNF is has all the properties of a CNF, which means it is a conjunction of disjunctive terms, and the disjunctive terms meet all the requirements. The other CNF is also the same way. So when you concatenate the two, when you have a conjunction of two CNFs, this is basically this operator here, or the implicit and operator right here at the blinky cursor, is what is connecting the two CNFs. So because each component is already a proper disjunctive term, so that means the concatenation of two CNFs remain as a CNF. All right, so we are now going to take a look at the resolution steps. So if I want to be really kind of systematic, then I go like, okay, okay, let me use another symbol here. So this not P and this P can resolve. So as a result of this resolution, let me just kind of pull this over here. So as a result of that resolution, I can now add a new term out of the resolution between those two, which is just going to be R plus false, or R of false, because we take whatever is left of one without the negation of P, and then we take the what is left of the other one without the P, so we are left with only R plus false, or R or false. Is that okay? Because this really is the essence of resolution. Okay, so if we're okay with this, then we move on to the next one and we ask, okay, is there anything else that can resolve with the not P of the first item? And this one only has a Q, it's not going to work, it's not going to work out. And then we look at the R from the first disjunctive term and we ask, do we see a not R anywhere else? The answer is no, we don't. So now we move on to this one and then we ask, okay, this is a not P, can we find a P somewhere else? The answer is yes, we do. It's right here. So now we basically add another, it implies another term, okay, which is not Q or false. The not Q is coming from this particular disjunctive term, and then yeah, and then the false is coming from this term over here. So what is left is not Q or false. Are we good so far? Okay, all right. So if I am just doing this, in a very systematic way, then I'm going to look at not P and see if anyone else has a P, and the answer is no. So now we move on to the not Q over here. So the not Q is going to go like, okay, does anyone have a term that is just Q? The answer is, yep, we do. Okay, this term is just a Q. So I'm not really working in the most efficient way, but the most systematic way. Um, so between these two, I will end up with not P or false, okay? Because when we look at this term here, the not Q is already used to do a resolution with this Q over here. So what is left is the not P from the first term and then the false from the other term, and therefore we end up with just not P by itself. And now we ask another question, which is, does this not Q resolve with anything else? The answer is no. So now we move on to the P over here, and then we are asking, do we have a not P, in terms of other terms? The answer is yes, we do. So now, we resolve the P in the P or false with the not P in the not P or false. And as a result of that, we now have just false because the P and the not P disappear in the resolution step. All that is left is the false or false. So technically speaking, I can write the false or false, but it is still false. So as soon as you arrive to one term that is false, the entire conjunction is going to be false because, in a chain of conjunctions, if one term is false, the whole thing is going to be false. So that means in this case, okay, what this means, okay, is psi and not phi prime implies false. But the but we know the implication itself has to be true. So if the implication itself is true, because of we proved that by in resolution. So if we know the implication is true, and we also know the right hand side is false, what does that tell you about the left hand side of the implication? Okay, let me ask that question again. If we know the result of the implication is true, and we know the right-hand side of the implication is already false, what do we know about the left-hand side of the implication? It has to be false. Hmm. Oh, I remember now. These locks work this way. There we go. So, so now we can now say, okay, this is false. It means psi and not phi is false. Okay. So what does it mean when psi and not phi prime, okay, forgot about the prime here, is false? Based on proof by contradiction, what does it mean? Okay, so let's go back and take a look at proof by contradiction, okay? So let me hide this first. There we go. So proof by contradiction is going back a little bit more. There we go. So proof by contradiction is basically saying if, okay, if psi implies phi, then we know that psi and not phi has to imply false, which means the conjunction itself has to be false. So knowing this conjunction is false is the conclusion, leads to the conclusion that psi implies phi. So in terms of theorems, okay, we know the phi prime is the theorem. So in terms of that observation, what can we conclude in this case? So let me go all the way back to the text editor here. So what does this mean? It means psi implies phi prime, which also means in this case, phi prime is a theorem of psi. Is that okay? So plugging everything back in. Okay, so let me go back and plug everything back in so that you can see the entire context. So what this means is this is our original psi. Okay, so let me just kind of write it out here. So the original psi is not P, or not R implies Q, and P or T. Okay, this is the entire psi. This actually implies phi prime. And the phi prime example is down here, right here. So this whole thing implies the negation of P implies not Q. So this is basically what we have proven, okay, is this expression implies this expression here. Are we doing okay so far with understanding, what we have just accomplished? So we're good, maybe? All right. So what if I were to ask you to write a program to perform all the resolutions? In other words, I give you a CNF, and you have to write the code to perform resolution until it hits a dead end, which means we cannot resolve any further, or until we get to false. Would that be a complicated program to write? If I tell you ahead of time that we have 5 variables, this is part of why CISP 430 is a prerequisite of this class. So how complicated would that program look? If I say, okay, you can use any programming language, how would you do it? No questions. All right. Can you do it by hand? Because this will be in exam 2. Maybe. Okay, we kind of need to make sure that we can do this in exam 2. Okay, so I'm asking you, do you think you can do this in an exam? Okay, I see some nods. Okay, I see some doubts. Okay. All right, so maybe we can take a look at, what the previous semester had for exam 2. Okay, maybe that will help a little bit. So I can go ahead and find that first file. And then this is CISP 440, the previous semester. This is exam 2. We'll take a look at one variation of exam 2 from last semester. And then we minimize this. All right. So we'll deal with the other one later. Okay, so this part here. So question number 6 is asking basically the same thing. We have psi looking like this, and then we also have phi looking like this. So the question is, can we use resolution to find out whether phi is implied by psi? Okay, so do you guys want to work on this? Or do you want me to work on it? Okay, yes, no, maybe. I'm not really listening to you. Yes, okay, very good. All right, so we are going to do some work here. Okay, this is psi. So psi is that which is already a CNF. In other words, you don't even have to convert it into a CNF. There's a different question to do the conversion. And then we have phi, which is pretty close to what we need, except it's just one step away from what we need it to be. Okay, so we'll go ahead and just copy that over here as well. So now we have your phi being that. Okay, what is the first step? What is the first step to prove whether psi implies phi or not? Go ahead. Negate phi. That is correct. So we have to figure out what is the negation of phi, which is the negation of whatever phi turns out to be in the first place, right? So we just take this entire thing and then we just go like, yeah, let's go ahead and just negate that, right? Okay. So do you notice something about this that is easy? We have double negation. So if you just take out the double negation, what do we end up with? I wonder. Yeah, we just end up with this, right? All right, so now we have to turn that into a CNF. Wait, it is already a CNF. That was the whole point, okay? That you don't have to do any conversion, at least in the previous semester. So this is no guarantee of what your exam 2 may look like. This is just what happened last semester. I'm always careful of not making promises that I cannot keep. All right. So now what do we do? What is the next step? So I think, okay, so what do we do now? Let's read the question again. The question actually gave you some suggestions of what to do next. So we'll go ahead and read the question. All right. So the question says, use the following area to show that phi is implied by psi only using CNFs. Okay, we got the CNF. We got CNFs. Resolution and proof by contradiction only. So these terms already tell you, or at least give you a clue of what you need to do. Okay, so at this point, what do we have is two CNFs. Okay, so let me go back to the question. Okay, we have two distinct CNFs. This is one, which is representing psi, everything that is known. And this one is the negation of phi, which is the negation of the theorem that we want to prove. Okay, so the concept of CNFs is almost used entirely. And then we also want to apply, resolution. Seems like that is an important concept, and also proof by contradiction, because those terms were mentioned in the question itself, right? So now the question is, what is the next step? I have two independent CNFs right now. This is one CNF, and this is another CNF. What are we going to do? Concatenate, or making a conjunction out of the two CNFs. So, but the reason why we are doing this is we are trying to see what psi and not phi is going to do. Okay, so that means, oh, okay, I can see that psi is a CNF, like so. And then we also see that not phi is also in the form of a CNF like this one. So now, we just go like, okay, so technically speaking, we are taking the conjunction of those two, right? But because they are both CNFs already, we can just go like, oh, this is just one longer CNF now. So now we look at this and then we try to perform resolution. All right, so show me what we are going to do in terms of trying to do the resolution. Say again. All right, so if we want to do it in a very systematic way, then we look at this not P and then we ask, all right, so who has just P, or who has P in the disjunctive term? So we go like, yep, this guy has one. So now we combine these two um, to a new disjunctive term. So at this point, because this one is longer, instead of spreading horizontally, I'm going to spread it vertically. So that means I'm labeling all of these as 1, 2, 3, 4, 5, and then it's easy to identify which one is being resolved which other one. So this is 4 and this is 5. Okay, there we go. And then I will turn off line numbers because it is definitely making things a little bit more confusing. There we go. All right, so Which two can resolve? So this would be number six. I think and one and three can resolve. Okay, one, three using P. So the result is going to be not Q or not R. There we go. All right, so I'm going to pause here and make sure that we all understand number six, why we can resolve using number one, number three, using P. Is that clear? We're good? All right. So now we move on to number seven. Okay, so what else can we do with between one and only using P, right? So we can say that, okay, no, how about number four? Nope, can't do it. What about number five? Nope, cannot do it. So now we move on to the second variable mentioned in number one, which is Q. So we go like, oh, one, two can do it, but we have to use Q in this case. So that means not P is going to be left over from one, and then R is left over from number two, and then we move on to, does anyone else have a Q? Yes, we have 1, 4. So using 1, 4, we can also use variable Q. So not P is left over from number 1. And then we have not R left over from number 4. And the last one is not going to work because not Q does not uh, resolve with not Q, so that one would not work. So now we can move on to number two. Okay, number two mentions two variables. The first one is Q. So now we go like, okay, who has a not Q? Five has a not Q. Six also has a not Q. So we'll do five first. But this is not necessarily the quickest way to do it. It is the most systematic way of doing it. So 2, 5 resolves to R or R, which is just R. Okay, so this is just R. R. There we go. And then we now move on to number 10. Let me just space out everything a little bit so it's easier to read. All right, so number 10 is going to be looking at 2 and 2 and 6. Okay, so 2 and 6 can resolve, and that would be using Q. So 2 is contributing R, and then number six is contributing not R. Ooh, are we done here? No, because R and not R is just one. It's just true, right? So that is not useful at all. Okay, because in a conjunction and you have one term that is a one or a true, it doesn't do a single thing. Okay, this is not particularly useful. Okay, what about 11? Who else can resolve using Q with number two? I think that's it. Okay, so now we have to look at 2 again, but this time using R for resolution. So you can see this is rather tedious, right? So that would become Q or P, or if I spell in the alphabetical order, it's P or Q. It would also work with number 4. Not particularly productive, but I think it is cool. So number 5, sorry, I take it back. Number 5 has a not Q, so we can use R so that it becomes Q or not Q. Or wait, okay, I think I made a mistake. 2, 3 using R is P or Q. Okay, that is correct. And then 2, 5. Oh, 2, 4 first. Okay, I forgot about 2, 4. Sorry, that was my mistake. So 2, 4 using R is going to give you Q or Q, which is just Q. Number 13, 2, 5 using R. 2, 5 using R is going to give you Q or not Q, Q or not Q, which is just one. Say again? Oh, right, the other one is negation. Thank you. That is correct. All right, so who else has? Hmm? What do you mean by resolution using two pairs? Hmm. So you're looking at 1 and 3. So 1, 3 is already explored. The result is not Q from the first one, and then just R, not R from the second one. Yep. Yeah, so I think what you might be asking is what if we have, okay, I think what you're asking is what about between 1 and 11? Is that what you're asking? Okay. Yeah, 1 and 11 can resolve, but it's a useless resolution because either way, you end up with true, which is not going to be useful. Yep. Okay. Yep. Very good. So number 4, 2, 4 using R is explored, and then this also has a not R. So we have 2 and 6, 2 and 6 using R. All right, so what do we have? 2 is contributing to Q, and then 6 is contributing to not Q. So Q or not Q is just true, which means not particularly useful. All right, number 14. So number 14, we are still looking at 2 and using R. So 2 has a R, we're still looking for a not R. So the next one up is number 8. Yep. Say again? Am I not using 5? 2, 5 using R. 2, 5. No, 2, 5 cannot use R because 2 is using R that is not negated. 5 does not have not R. It has R also not negated. So those two cannot resolve. All right. So how about 2, 8? So 2, 8, 2 is contributing, okay, using R. So 2 is contributing the Q, and the number 8 is contributing not P. Okay, so we'll redo this using alphabetical order, like so. And then we move on to number 15. 2, okay, we are up to 8. And then we have 10 is useless. Okay, so don't worry about 10. I think that's it using R. So now we move on to 3. So are we doing okay so far in terms of the process? Now, in the actual exam, if you spot a quicker way to get to the false, okay, you can use that. But to show that you cannot get to the false, you have to go like systematic. So might as well just do it systematically. All right, so what about 3? What can resolve with 3? So everything that has a not P can potentially resolve with it. So basically, it just kind of keeps going like this. Are we good so far? So do you guys want to know what the answer is? Maybe? Because I can show you the entire answer. The answer is actually it does not resolve. So if I show you the key to this particular version, that's the whole sequence of all the resolution. Um, Basically, it shows you which one can resolve with which one, resulting in what. And oh, okay, I take it back. I was wrong. You can actually resolve the whole thing because it ends up with nothing inside the parentheses. So it just takes a few more steps to get to that point. But it is very systematic. Okay, this approach is very systematic. So if I go back to the document that we have and just kind of lined it up, with the key generated by the program, you can see that it is almost exactly the same. Well, close, not exactly the same because I think the ordering is off by a little bit, but it's a very systematic approach. You can also see how the 000, which is 1, because in the program in the key generator it was 0 oriented, but when I am doing it by hand it is 1 oriented. But otherwise the structure is very close. So we are really just a few steps away from resolving to 0. Do you guys want me to do it? Say yes. Okay. All right, so we are now on to 3. So 3 is basically the same as 2 here. It can resolve like a few times. All right, so we'll finish the whole thing. Why not? Okay, so 3 has P, and we have the not P's over here. So we just have to go like 3. Now with this one, everything that resolves to just true does not even show. So maybe there are a few more steps, in between, but we'll still do it. We'll still do it systematically. So using P with 3, um, we're looking for not P. The first one is number 7. So 3, 7 using P. 3 is contributing not R, and then 7 is contributing R. So that whole thing is just 1, which is not productive. Number 16, 3, blah, 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 using P. All right, so who else can do it? Okay, we are up to 7, so 8 can do this too. But using 8 is also not particularly useful, but it is kind of useful because we just resolve to not R. This is because number 3 has not R in it. Number 8 also has not R in it. P versus the not P, that goes away. So we have just not R left. So at this point, okay, if you are, if you insist in using the very systematic way of doing this, you can keep going. But on the other hand, you go like, I think we can stop now because if I just look at number 9 and, oops, this is derivation number 17, which is based on 9 versus 16 using R. Okay, now we have false. So the whole thing is done. It is resolved. Is that okay? Do we understand the approach of doing this? All right, cool. So that's pretty much what your next homework assignment is going to be, is just doing the resolution and also a little bit of CNF. Um, so we are pretty much done with um, resolution. I mean, propositional logic. Yes, propositional logic is pretty much that. All right. So getting back to, so the key is really converting a general Boolean expression into CNF, because this part, okay, if you don't call this mechanical, I don't know what else to call it. It is very mechanical. Okay. Now, writing the program to do that may not be easy, especially in C++ or Java, because I personally do not like to use those languages for processing anything like this. But for the most part, it is fairly easy to do using a scripting language like JavaScript or Python. This is like not too much of a challenge. Um, okay. So the key is converting a general Boolean expression into CNF. Is that approach really difficult, or do you already see a structure of how to do it? I'm assuming that you guys have started on the homework assignment to convert a Boolean expression into CNF. Okay, I see someone shaking the head. Okay, so tell me more. You have not started. Okay, because okay, yeah. So there are certain things that we have to do when you are converting. All the implications uh, become ors, where the first component is negated. That is mandatory. You have to do it. Okay. Whenever you see there's a chance to apply De Morgan's law, that is also mandatory. Okay, you have to do it. Okay, so that means a few of the rules are going to be applied until you get to the point where those rules cannot be applied anymore. Then it's a question of distribution, because what is left is usually a choice of which distribution do we use. And that part depends on what is already there versus what we need it to be. Okay, so I cannot explain any further. Okay, by the time you turn in the homework assignment next Monday, then we can talk about how to perform, how to choose which distribution to use. But guess what? There are only two distributions. So you can try one, try the other one, kind of have two parallel paths and see which one works out. Okay, because very quickly you'll realize, oh, in this situation, we're going to use this distribution. in that situation, we're going to use the other distribution. Okay, so it will be fairly clear. Yep. Yeah, absolutely. Yep. All right. So we are going to move on to the next module at this point, unless unless someone in this class has a question. Yes. Number 17. Okay, look at it this way. Look at this as R or false. Look at this as not R, also or false. So when you resolve using number 9 and number 16, um, you basically get rid of the R from this one. You get rid of the not R from this one. So what you end up with is false or false, which is false. Because one is a R, the other one is a not R. Because number 9 is just the R. Number 16 has the negation of R. So it still fits the pattern of resolution. Yep, join the two without any mentioning of R. Yep, yep, go ahead. No, until you find the false. If you find the false like what we have now, you can stop right away because any further resolution is not going to change the false to anything other than false. But if you cannot derive the false, then you have to keep going until you exhaust all the different ways of resolving. Then, well, no, because what you are proving when you cannot resolve to false is simply that phi is not a theorem of psi. That is the only conclusion. So I'm not sure I understand your question. Are you talking about the conclusion of not resolving to false, or are you talking about? Go ahead. Okay. Uh, Point to a line that you find confusing, and I'll try my best to explain it. Yes. So the idea. Okay, so let's go back to the whole point of resolution first, and then we'll go from there. So I think resolution is going up, 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 right there. Okay, so this is resolution. We have we have used we use Boolean algebra to prove that this implication is always true. So what we need is to find two disjunctions where in one disjunction we have a term that is just generally called psi over here, whereas in the other disjunction, it has exactly the negation of the same side. That's what we're looking for. So when we look at each successful use of resolution, we'll just pick a random one. We'll pick number 11, okay? So when we look at number 11, we are basically looking at number 2, which is this, and we're looking at number 3, which is this. So in this case, if I say R is our psi over here, then the not psi is just going to be the not R over here. So we have found a connection. We have found a connector between the two disjunction. So using the same pattern over here, it means whatever is left other than psi from the first disjunction and whatever is left not counting the not psi from the second disjunction, we'll just kind of put those into one single disjunction, and that would be the result of the of applying resolution. Yeah, yeah. It's not simplifying the CNF. It is more like generating a simpler term to the CNF. It is implied by the original. Yes. Well, but we keep appending, right? Because everything that is implied from the application of resolution, you can stack those into the conjunction without changing the possible outcome of the conjunction being false. Let me say that one more time. Okay, so let's say we have a term P, and then okay, let's not use, yes, it is, it is still being implied by the original conjunction, yes. So if this concatenation, if when you look at this, seven, not counting the last one, okay, when you look at number one all the way to number 16, and you make that gigantic conjunction, it is still preserving the value from the original CNF, because every single step we are just adding one more term that is implied by the original one. Is that okay? Okay, let it sink in a little bit, okay. But how about procedurally? Is it okay? Okay. So the only one I need to point out is number one cannot just resolve with number 11 and get to false right there. Okay. So let's take a look at that. Okay. Because I think it is kind of important to look at that. So we'll just say that, we are looking at number one versus number 11, but then you have to tell me which variable do we use to perform the resolution. Now, you have a choice here, right? Because if you look at number one, it has not P. Okay. Number 11 has P, so you can use P. So you have to tell me which one you're using for the resolution. So if you're using P as the connector between the two, then you end up with Q, not Q or Q, which is false. On the other hand, if you look at the same two disjunction, but this time you're using variable q as the connector, then you end up with not p or p, which is also just true. So that means neither resolution gives you something that is useful, because it just said, okay, if you resolve these two, it's just giving you true. But the value true in the conjunction is not useful, because it is the identity of conjunction. So are we doing okay so far? All right. Are you getting distracted by something? Do you want me to stop the distraction? Is okay? All righty. Okay. So, hi. Hi. I'm talking to you. Are you doing something that might be distracting to other people sitting behind you? All right. Okay, you're okay? All righty. You're just looking at the head bobbing. Okay, gotcha. All right, because I do want to make sure that we don't end up with people getting distracted because of some other people. I get it. I'm the same way. Yep. This entire thing is a huge, gigantic CNF. So so what we are saying is, okay, let me just give you the original form, okay? So we'll go ahead and start with, so I'll give you like the first five terms, right? So let me do it this way. I'll just copy and paste it. All right. So we have these five terms, okay? That's the original, right? This is the conjunction of psi, which is everything that is known to be true, and the negation of phi, and phi is the theorem that we want to prove. Is that okay? So now we just pick two of those, okay? We'll just say one and three, okay? So we look at one and three, and this is one. So I'm really doing this step by step, okay? And then we look at three, which is this. Is that okay? So we look at these two and go like, hey, it matches this pattern over here. So anything that matches the pattern of the left-hand side of the implication can now be used and go like, okay, that implies the resulting disjunction which is getting rid of P, and then we have not Q or not R left. Is that okay? Okay, so now the question is, can we append not Q or not R to the original CNF so that if the original CNF is going to imply false, then the bigger, longer one will also imply false? That is the question. Okay, so now the question is, okay, so the question really is asking if X implies Y, okay, what happens to X and Y? So we know the implication is true, okay? And two of these components is implying this component over here. So now the question is, what can we say about the whole thing? Okay, we'll introduce one more thing, which is Z, which has nothing to do with Y or X. So we want to see what is going to happen here. Are we doing okay? All right. So now we just have to, okay, what is the tool that we're going to use? Truth table. Okay, so we're going to use a truth table here. Okay, so the truth table is we have X, we have Y, we have Z. So this is going to be a little bit longer of a truth table. So it will be something like this. Okay, so those are because X, Y, Z are quote unquote independent, right? But out of this, they're not truly independent because we already know that X implies Y. That has to be true. So now we basically say, okay, so if X is implying Y, so only certain of these rows are actually applicable to us because if X and Y are both 0, yeah, that would be fine, okay? If X and Y are both 1, it's fine. If X is false, every time X is false, it's going to be okay. This is not okay. So we can ignore these two rows because X does not imply Y on these two rows. And then on these two rows, X implies Y is true again. So now that means, from here on, we do not look at these two rows anymore. So now we look at XYZ, at the conjunction. Okay, so we look at X, Z, Y, or XYZ. It doesn't matter because it is a conjunction. So we look at the conjunction here. Okay, obviously this is false. So anytime X or Y or Z is false, the whole thing is going to be false. Okay, and this is the only time the whole thing is true. Are we doing okay so far? Okay, so now the question is, um, and then we also look at X by itself. So when we look at X by itself, on all of these rows, X was false to begin with, but then the conjunction of XYZ is also false. And then when we look at this row here, X was true to begin with, but then when we look at the conjunction, XYZ is true as well. So that is the reason why we can perform the resolution steps. And then every time we perform a resolution, it is giving us a new term. But that new term has a property. It is implied by the old terms. And we can keep adding those old terms to the conjunction so that we're basically adding more fuel, okay, as we go along. But every time we have a combustion to create even more fuel, which does not work in chemistry, but in this class it does, we are continuing the whole thing because if X implies Y, then it doesn't matter what Z is, okay, which is the rest of the conjunctive normal form, we are still preserving the original value of X, which in this case is is the conjunction between psi and not phi. So this X here, let me just kind of make sure that we write this down, okay? X is representing psi and not phi, and then Y is representing the result of a resolution step, and then Z is just whatever. I mean, it's the other terms that we stack on. Is that okay? All right. So I think the truth table is really useful here because it shows you, at a very mechanical level of why we can keep stacking those additional terms from resolution. Because every time you add a term from resolution that is implied by at least two of the previous terms, it doesn't really change the value of the original CNF. And all we want to do is to show that the original CNF is false. So is that helping a little bit? Okay, all right. Are we still doing okay? Any other questions before we move on to the next major module? The next one is independent. Yeah. So the next one is independent because the next one, according to the ordering, hmm? Counting. Yep. It is as simple as counting. It's like tech. I think we know how to count, right? But counting is kind of the whole point of this entire class, okay? Well, not the whole point, but a major point, okay? So when we look at all of these terms, it's like, no, no, not these symbols again, more symbols. So instead of looking at the symbols to begin with, let's talk about lotto, okay? Yeah, I see that most people are now going like, okay, we want to talk about lotto. So let's go take a look at the Lotto website. Okay, Super Bowl, and yeah, this is yeah, Super Bowl Lotto lottery. Hmm? I have never bought a single lotto ticket for my entire life. Hmm? Why? Because it does not make sense. It is not pessimistic. It is statistically not sound. Nope. I have never gambled. Now, it does not mean that I have not been to a casino. Okay, that is a two different thing. I go to a casino. Go ahead. Hmm? Am I what? Card counting? Oh no, no, no. If I go to a casino, I hit the arcade center and I play Street Fighter because I know how much time a single token will last me, even with challengers. Because newer kids, the younger generation, they don't know how to play the old characters anymore, and I do. So they just go like, "I'm gonna challenge you." Oh, really? Yeah. Hmm? See? Okay, I'm not quite catching what sports betting. Nope, I don't do that either. I don't leave anything to chance, or try not to. Hmm? I would say it's more reliable than any Jeep Wrangler that is on the lot. I am still gambling, but it is the best choice that I have. No, it is, well, okay, it is not a gamble. I make my decision based on distribution of probability. Yep. So it is I have already sufficient data to show that in the cost benefit analysis, it is leaning on my side. Okay. So you go to a casino, okay? You go to a casino. The first conclusion is chances is not leaning on your side. How can you tell? Who's going to pay for all the electricity? Who's paying for the people who vacuum clean the carpet? It is money from the people who gamble. So tell me that it is not leaning on your side. Yep. Say again? No, there will be no Mitsubishi in my life. Uh, Many years ago, maybe. Yes. So if you're talking about the early Evos, maybe. Yep. I don't think Mitsubishi has made any really useful or, yeah, exactly. In the past 20 years, exactly. The really old ones, yes. Okay, even Isuzu also makes really good SUVs back then. Yep, a Forerunner. Yeah, but the Forerunner, unless you get a really old one, there has Forerunner ever been solid axle? Okay, we are now talking about cars. Okay, okay. Last word, Land Cruiser. Okay, that's the holy grail. The old 80 series. Land Cruiser. That's the one. Okay, but I cannot afford it, so it's not. So this one has nothing to do with probability. It has to do with affordability. Hmm? Invest, but investment is not a gamble. Okay, so in terms of investment, it's the same thing as gambling. So you basically go like, okay, what are the billionaires telling us to invest in? Let's think. Jensen Huang is saying invest and buy stock in Nvidia. Okay, so how does he make the money in the first place? Having people to buy stock in this company, right? Or Elon Musk, saying, okay, let's invest money in X or Tesla and so on. Okay. And then everybody's going to buy gold, right? Until we see an asteroid in outer space, and then we go like, let's go mine that asteroid, and which is entirely made out of gold. And then suddenly the price of gold drops to nothing. Yep, historically that is true. Yep. And I think it will kind of do that. So with investment, I know we are stepping away further and further away from the class content, but in investment, the most important consideration is your time horizon. Okay, so for most of you who are significantly younger than I am, and if you're investing or if you're budgeting your life properly, then you have a long horizon, which means, well, even if the stock, S&P 500, for instance, is to suffer and kind of blow up, for a year or two, if your time horizon is 30 years, it's like, okay, whatever, right? Especially when it drops, you invest a little bit more. Anyway, getting back to Powerball, not Super Bowl, but Powerball. Well, okay, I can easily explain why that is the case because education, especially K-12, we receive lottery fund. Yes. So thank you for our sponsor. Yes. Yeah. All right, so we're going to look into lotto, okay? So the next jackpot is 273 million. So the question is, should I buy a ticket today? Okay. Hmm? What? 770? Well, wait. Okay, let's one step at a time, okay? One step at a time, okay? So how do you determine whether it is a good time to buy a lotto ticket or not? Okay, that's a simple question. How do you decide whether today is a good day to buy a lotto ticket or not? Hmm? Say again. So we'll start with how, and then we'll get to the why. So how do you decide whether today is a good day to buy a lotto ticket? Okay, you look at the jackpot. The probability actually changes depending on the jackpot money. I'll explain that later. But for the most part, you look at the jackpot money and ask, okay, so if I buy a ticket today, is my chances of just making the $2 back, is it just even? Okay. because you need it to break even. Okay. So now, in order to do that, in order to make that determination, you need to understand the rules of the game. So we'll go to, look at the how to play, okay, right there. All right, so how to play is pretty easy. You can pick five numbers between 1 and 69, okay? So you have to pick five of those. Now, it doesn't really say anything about uniqueness, which means, can I buy a ticket that is just, 55555? The answer is no, okay? You cannot buy a ticket with only five fives on it because they have to be unique numbers. Okay, so that's the first thing. Is it doesn't quite tell you that, but it has to be five different numbers. So this pick five numbers is actually implicitly saying five different numbers. All right, and then on top of those five numbers, you have to pick one number between 1 and 26. Okay, so now the question is, how many tickets are out there? In other words, how many different tickets are out there just based on this analysis? So we'll also just say that ordering is not important. Okay, ordering is not important within the five numbers between 1 and 69, which means a ticket, so you can fill in the ticket yourself, right? So if you buy a ticket and you wrote down 1, 2, 3, 4, 5, and then somebody else wrote down 5, 4, 3, 2, 1, they are considered the same as far as those five numbers are concerned. Is that okay? Ordering is not important. Okay, so we are dealing with, yep, go ahead. So when ordering is important, it is a permutation. When ordering is not important, it is a combination. Very good. All right. So now the question is, how do we do that calculation? Okay. So we are going to start with something simpler. Okay, because picking five numbers from 1 to 69 generates a lot of possibilities. So we're going to go with something that is a little bit more humble. So we're going to go like, okay, let's just look at I'm going back to my text editor here, right there. Okay. So instead of dealing with a huge number of things, okay, let me make a separator because we are done with that topic. All right. So we're gonna say out of the possibilities of 1, 2, 3, we want to pick two. Ordering is not important, and I would say pick two unique ones. Okay. So are we understanding the question? Basically, I'm putting 1, 2, 3, or three marbles, okay, labeled 1, 2, and 3 in a bag, okay? And I'm asking you, okay, pick two, balls of marbles out of the bag. So I'm asking how many ways can we pick two marbles out of the bag that has three to begin with? Okay, so we'll take a look. Okay, so we're gonna say in the order of picking, okay, you can say, I'm going to pick number one or number one marble first, and I'll pick number two marble out of the bag. You can pick one and three, you can pick two and then three, you can also pick uh, two and then one, you can also pick three and then one and then three and then two. So these are the orders of picking the marbles out of the bag. But I also said ordering is not important, right? So when ordering is not important, 1, 2, and 2, 1 are really the same thing, right? So if I want to label the unique combination, this is combination A, which is really the same thing as this combination A over here. This is combination B with 1 and 3, but 3 and 1 is also considered to be the same combination. And then this is combination C, which is the same as this combination over here. So are we understanding that there are six permutations, but there are only three combinations? Is that okay? All right. So what about we just bump it up to four? Okay, 1, 2, 3, 4, and we're gonna do the same thing. Pick two unique ones, and ordering is not important. Okay, how does the analysis go? Kind of the same thing, except a lot more tedious, right? So 1, 2, 1, 3, 1, 4, 2, 3, 2, 1, 2, 2. Oh, no, we gotta have 2, 2 because they have to be unique. 2, 3, 2, 4, and then we have 3, 1, 3, 2, 3, 4, and then we have 4, 1, 4, 2, 4, 3. Those are the um, permutations. So now we have to identify the combinations. So 1, 2 is a combination. That's one. And then we have 2, 1, which is also a combination. 1, 3 is a combination B. 1, 3, 1 is also combination B. 1, 4 is combination C. 4, 1 is also combination C. And then we move on to the twos. 2, 3 has not been seen before, so it's E. But 3, 2 is the same combination. 2, 4 is has not been seen before. We've called it F. So 4, 2 is essentially the same thing. 3, 4 is a new combination. We call it G. And this is also going to be G here. So we have, I think I'm missing something here. Okay, we have A, B, C, D, E, F, G. So we have seven. That doesn't make sense. Huh? I don't have G, D. I'm missing D. Okay, okay, now it makes sense. So there are six combinations. So the question is, um, if I want you to calculate the number of combinations for picking 5 out of 69, are you going to do it this way? Because that would definitely be a not good use of your time. Okay, so now the question is, then how do we do this? So we need to somehow come up with a way to do the counting, but without listing everything out. Okay, so the first thing is deal with permutation first. Okay, so we're going to deal with permutation first. So permutation is basically saying, out of a set of something, okay, pick, two or three or whatever, and ordering is important. All right. So that is actually very systematic, okay? Because if you start with a one, then the next choices would be only two, three, or four. If you start with a two, the next choices would be one, three, and a four. If you start with a three, then the next choices can only be what? One, two, and four. If you start with a four, the next one that you can choose can only be what? Two, three. Oh, I forgot. One, two, or three. Does that make sense? Okay. So let's just say that we are now saying, okay, let's pick three then. Okay. So if you try to pick three, if the first two are one and two, then you only got three and four left. Does that make any sense? If you choose your one, three first, then the next one can be a two, can also be a four. If you pick one and four first, then the next one can only be two or three. If you pick two and one first, then the next one can be a three or four. And if you pick one, two, three first, then the next one can either be a one or four, and so on. Do you see a pattern? I hope you do. Okay. It is a tree. I'm trying to make a tree out of text, out of just a text editor. So the first, okay, so consider this, okay? Imagine you have a root node all the way over here. So the first fan off is four because you have four things that you can choose from for the first item. Whatever you choose as a first item, you only have three items left in the bag. So that's why the fan out of the second level is three, 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 three. Is that okay? Once you have picked two out of the four items, then you only have two items left. So that's why the third level, the fan out is only two. Is that making any sense? So that means if I generalize this whole thing and I say, okay, we have n items of which choose m unique items, what do you think is going to be the permutation, the number of permutation? The number of permutation is, yep, That is correct, but we can also look at it in a slightly different way first, because we're basically saying the first level, there are n of those. The second level, we have n minus one of those, right? The third level, we have n minus two of those until we get to n minus m, right? So that would be the number of permutations. Okay, so we'll just go ahead and say P of nm is defined like this. But it doesn't look very clean like this, right? So we go like, okay, what about we look at this as n factorial, which has some extra terms that we don't need, but we're going to divide it by m factorial. Aha, that will solve the problem. Okay, now does it solve the problem? Because m factorial is going to, let's see, yeah, so it will solve the problem because the next one here is n minus m minus 1 factorial. I think, no, I take it back. Let me think. Mm, no, it is correct to be divided by m factorial. Hmm. We choose m of those. Okay, something is not sticking in my head because I can't see the equation like this. Okay. Ah, okay. Somebody left behind some pen here. Okay, so we are looking at n times n minus 1 times n minus 2, blah, 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 all the way up down to n minus m. I think it also has to be a plus 1. Okay, and then the next item is going to be n minus m itself. Okay, so we have n minus m all the way down to 1, but this is just, um, this portion is n minus m, the whole thing factorial. So I think this is correct because we are choosing m of those. So I think that is correct. Hmm? Yeah, so that seems correct to me. So that means P of nm is n factorial divided by n minus m, the whole thing factorial. That makes sense to me. Yep, yep. So from the mathematics perspective, it does make sense. But then there's also a different perspective, which is of all the combinations that we can come up with, um, no, this is correct. Okay, this is the way it is. Okay, so now the question is, what about the combination? Okay, so when you look at the combination, um, you are basically saying, okay, I need to rule out all the duplicates. Okay, so we are going to start with P of nm, and then we say, how many duplicates do we have in the number of permutation? In other words, one combination, for each combination, how many permutations can we get out of it? Let me say that one more time. Okay, I know it's close to 420. So let me repeat the question. If I need to pick m items out of n, okay, and I really just want to know the number of combination and not the number of permutation, the question is, can I derive the number of combination out of the number of permutations? So look at the picture that we had before. Okay, look at this picture here. So, or this one here. So now you look at this and go like, okay, for every combination A, how many permutations can we get? Every combination only has two items, right? So for two items, how many ways can you rearrange the ordering? Only two ways. Why are there only two ways? Because because of the same reason. For the first item, you are so only for two items. The first item is, you have two choices. But for the second item, you only get one choice. So that means if I know that each combination has m items, then for each item, for each combination, there are m permutations. So that's why we divide the whole thing by m. Then we basically we reduce the number of permutations to the number of combinations. So when you expand this whole thing, it becomes n factorial divided by n minus m factorial times m factorial in the denominator. So there are ways to look at this, okay? But the best way to look at this is the m factorial is accounting for each combination there are m factorial permutations. So when you start with the number of permutations, you divide it by the number of permutations per combination. Okay, I didn't bring my laptop, my tablet today, so I can't really show you in the tree format. But next time I will bring my tablet because I did not anticipate to actually get to this topic today. So, but read the module. Okay, the module actually explain all of this stuff too. So the module is counting, and that probably will take some time already just for counting. But if you finished counting and you have some extra time, you can also go to discrete probability. Huh? Say again? The next exam is going to be on everything up to and including propositional logic, but not usually with counting. Hmm? In the syllabus, it says 2/3 of the semester, which is about week 10, 11-ish. Yep. Yep, we'll finish it, okay? But I don't want to draw a tree of 69 items, choose five, because that's going to be very time consuming. So this is why we want to derive the equations first, and then we will work with the equations. So you're correct. We are going to talk about the Powerball thing, and then at some point we'll talk about why it is never a good time to buy a lotto ticket. Ah, okay. Well, not only is a big number, but you can have duplicate tickets too. So that means you can have multiple jackpots. And the chances of having multiple getting the jackpot increases when the jackpot goes up because everybody thinks the same way. It's like, oh, it's worth it to buy it now. So we'll address that also. We can actually develop a model of how the number of tickets get sold ramps up with the jackpot number. Hmm? Yeah, 1.8 billion is nice. So how many people win the jackpot that time? So two people. So with two people, they have to pay enough taxes. So each one is almost not really making that much money. I mean, it is a money. It's 9 billion, right? Yeah. So $9 million is still a lot of money, but taxes, means a lot of that money is gone, because we are not looking at the chances of winning. Excuse me, I take it back. We are not looking at how much money the people win, but we are also balancing that against the probability of winning. Yep. Oh. Very nice. Well, it's a good introduction to the topic, because most people understand what it is about, and they have at least some kind of an interest to know the probability. So, yeah. Also depressing because they would realize that there's no win in this situation. Yep. Yeah.